about? It's superheated. It's superheated refrigerant. Wait, am I stupid?
Refrigerant 22.
Why are there two different refrigerants?
That one.
Oh my goodness, Dave.
It's further down.
Why?
That sound is awful.
Sorry, guys.
Yeah.
Okay.
Let's see if I can filter it a little.
Can I just pretend it's refrigerant 22?
I'm sure if you write it into the question, like if you copy the question.
No. What you guys get for your value?
Hello.
So if you want to just write down my table.
Low-key. I did all the work. I used the wrong word.
Okay. We'll give that a shot. I'm still having trouble with my microphone. Nice. Get that up.
My friends have ruined any terrible
What? I can't tell you 9 from your 4. What's that say? Oh, 267.
I need to figure out how we got that specific heat for water.
You Google it, and it's like a well-known number.
But when I Googled it, I got like 4.2.
That's exactly what it is.
But why did you tell me it's 4.1?
Okay, it is 4.18, but you rounded 4.2. Yeah.
Alright, cool. So today, I think we can finish homework 1. Quick recap. We had mu n, mg, b times v, n, mg, n, mg, and then kx. So MA equaled negative mu mg, MA equals negative BV, MA equals negative KX. That was like mostly what we were kind of working on last class, of like trying to get to that step, because all of these were all equal to MA, 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 equal. Good so far? I'm just kind of like going through a little, just, and then in part A, since A equals negative mu g, and this is a constant, now we can say, all right, well then kinematic equations work. So x of t equals x0 plus b0t minus mu g t squared over 2. And we could get there by integrating that constant number twice, or I mean we have that kind of banked away as the kinematic equation for position. In this one, in part B, we had to do a little extra legwork because now we're looking at integrating a function that is a function of itself. So dv dt is negative bv. And what we found was, like, after integrating twice, we'll do the magic arrow. And I think it was -1. Yeah, like that. something like this.
Because you have a negative out.
So far we've seen like two things. No?
There's no X out, but you're turning back minus plus. Because there's a negative on that.
How am I doing? Is this not what we did, or this is what we did?
Wait, why
What do you think?
exponential?
All right, we'll stop there. See what you have, because I'm just sort of flying through what we did on Friday, but we can catch up.
I like finish right here.
Yeah, that's what I remember. It was like
No, because you have to integrate
Why
it twice,
integrate
and then
it
you
one
integrate from
time?
exponential to x.
Or go just copy it down.
It has to be good as I.
Okay. That's it.
Yeah.
Why is there no exponential term in the second part B?
No
Just
exponential.
I know, I copied what we did during last class. At least I think.
Yeah, there's no exponential terms.
Right here,
Where?
like x e to the negative b over m.
Like
No,
plus
just
x
you have
zero.
plus x0. I mean, I guess it doesn't matter here because x0 is 0.
Oh, you want to say like
But in general, shouldn't you have?
plus an x0 over here?
Yeah, I'm curious.
We can do that.
I'm curious if you're supposed to.
Yeah, because really,
I know it doesn't matter here.
really it's x of t minus x0 equals that. Because we end up with like an integral of dx from x0 to x of t. It's that right hand side. Yeah. Yeah, that's a good call.
Because he's minus MB over E.
Oh, okay. I just took the negative.
Yeah. Or distributed. Well, I took pictures of some of the guys. Some of them. Oh, okay. It's like these are. What is that?
I don't be scrolling. That's cool.
Yeah, they're all like this.
They're all like that. Wow, they're all pop
Well,
shapes.
that's one of the. So there's a complete one of those.
Oh, they're all pop shapes. These are looking kind of rare.
So there's all those. Some of them are like the shiny.
Holographic, just.
Some of them are doubled up. Like some of them have multiple cards. And then yeah, they got the weird.
See, those are low-key rare. Those are also each.
And then they got all of these. There's like.
They came with the VHSs.
So yeah, TV cards. Yeah, actually, I think got a bunch of these.
I like this panel.
No, is it?
These are
Yeah, those are Japanese.
Yeah, so there's a bunch of these ones. I like this guy.
Shelter.
Yeah.
He's a silly guy.
And
It's all Ken Sugimori art too, which is kind of cool.
that's fun. And that's all the picture looks
That's cool.
but it's there's a lot.
No.
They're all pop shapes. They're not expected.
Yeah, so it's kind of like they're not cards to be opened.
No.
So he was like my dad bought the whole thing.
MC over in.
That whole line.
There's definitely some of those are well over $5, like the Charizard or the Sabrina.
So I have a guy who like does eBay. I bought like selling company, and they do a lot of cheap.
Oh, you're telling me.
So I might ask him like value wise.
Some we also go on TCG player.
Yeah, because some of the plastic pages are starting to degrade, and
Yeah.
I don't want to damage the cards, so I might try to buy all the individual sleeves because then in the binder, like they can also damage.
You can buy penny sleeves. You can literally get 100 for $1.
Yeah, so like I might just get a bunch of the penny sleeves.
I have just like a shit ton of penny sleeves because I collect.
Yeah. So I might invest in some penny sleeves and just like get one of the boxes that holds the individual cards. Put them somewhere else. Like I'm gonna slap them.
slap them all, slap grade every single one of them, with 0 to 10, what I recommend. Don't grade anything. Don't grade anything unless it's like your favorite card.
There's like hundreds of cards that would be like,
None of the cards that are have been in a binder for 20 years.
Alright, we're good? At least I think we're good. It seems like we're on the same page so far. So then part C, we have A equals negative K over MX. Or another way to write this is like X double dot equals negative K over MX. Have you seen an equation like this where acceleration, and it also comes up in like our like resistor, inductor, capacitor circuits, same kind of equations come up. But how do we deal with this? Like the fact that the second derivative is equal to the actual function. Like at least like times a constant.
Don't look at me. Take a surface interval.
What if you make a surface?
Gaussian surface? Kind of.
Gauss surface. That one's a little overkill. If we're doing like surface integrals for like these like second order differential equations. That one's good for like boundary value problems. Take the surface integral, turn it into a volume integral. How do we deal with this? What do you think?
Yeah.
What is x of t? What do we do with that?
You can integrate one. That's for certain.
Wait, you did you do it on one ago?
there's an easy way to do it, but I don't know.
What's the easier way to do
I
it?
don't know. We learned it.
Hey Jarvis.
I'm definitely simplification.
Have you seen this before? Like, do you know?
I don't think I've done like double second order derivatives, but like first
No,
order.
we have not done the second order derivative.
No.
Like this kind of equation where it's like
Yeah, you like
a
make a sort of
double the
function,
second derivative is
and then you just multiply everything by like one function, and then
Do we just
integrate the zero.
that's what we're trying to do. Like we're trying to integrate twice, but it's hard to do. It's hard to separate the variables because we have like a d squared,
Over 3.
dt squared,
Yeah.
and
But like, but also
it's hard to get like two integrals at the same time.
I have no idea. I don't know if we were supposed to learn physics or did, or if I'm just stupid, or both, but like, I have no idea.
I mean, that's it, guys.
Well, if I remember from, now mechanics was doing
If you need to copy down the question, I don't know how to do
Which
it.
one was teamwork? Which kind of teamwork?
I don't know how to do this.
Yeah, because we still end up with d squared.
But like we've done the,
Yeah.
If I remember from physics 1, it's like simple harmonic motion and then like sine and cosine.
That's okay.
Yeah, I've never seen it.
I didn't take physics 1 with calculus.
d squared.
I definitely didn't take physics 1 ever, because I didn't
yeah.
Okay. How do you
We
integrate?
just get the Van de Graaff generator now. Oh god, look at that.
Look at this bad boy. Whoa.
Isn't it really you like
My physics teacher is also my physics.
so you're just like gonna grade the first time and then whatever.
He's not a
But that one was kind of nice because we
we
had
call him safety.
but now we got d squared. D squared.
He's
Our principle is pretty
I don't know, I just worry.
Well, like,
The other administrators were not such like.
he's not a bad guy. Like don't get me wrong.
Who? Ah.
My principal got the star in civil and
Yeah, K over M is
That was short.
there's a constant.
No, well,
Two derivatives of x.
like we had filmmaking class. Oh, one time for my English class, I got him to give like one of those presidential video messages for this video I made. It's like I'm the principal of the school. I approve existence. So that was the first instance where he appeared in my English school. And then there's like
I was in a short. I helped make a short ago. In high school. It was like a 20-minute long little thing. It was terrible. But it was
Had a lot of heart.
yes. I think we should watch it.
And then there was a second movie he appeared in where he was like the prime detective of some kid who was like stealing the food.
Alright, so I didn't expect you to like come knowing this information. And even if you did, like you might have seen it in passing, now you're being asked to apply it to like physics and engineering. But let's try something. What's a function where if you take a derivative, you end up with the same function? E to the x, right? So let's say that it's like e to the, I don't know, lambda t, right? Just where lambda is just something. So now x dot is lambda e to the lambda t, x double dot is lambda squared e to the lambda t. Something like that. Would this work? Could we plug that in? If I just said x of t is e to the like lambda t. Is there anything missing so far?
There's no value squared next to the x.
But we could take a square root, right? We could just say like k over m is lambda squared, so lambda is root k over m. That would work. Is there anything else missing?
There's no t in the original acceleration equation. No.
Oh, it's all t. Everything's t.
Oh.
Like x is a function of t, so acceleration's a function of t. And this is something that is kind of weird, and I'm glad you pointed it out, is like all these variables, they're all functions of time. Like unless they're explicitly a constant. So like k is a constant, m is a constant, but acceleration is changing over time. Position changing over time. So they're all like some function of time. They're related to each other, right? Like we can still say a is the derivative of v is the derivative of x, but everything is changing with time. Makes it more interesting. It's more fun that way. And like change is the spice of life, right? All right, so then let's try it. X double dot equals lambda squared e to the lambda t, negative k over m, x equals negative k over m.
Is x in the denominator or is x being multiplied?
That one's multiplied, yeah, like kx over m. So now what do we end up with? What is lambda? Yeah? Really, it's like plus or minus, right? Plus or minus negative k over m.
You can move the chat box.
Oh yeah, let's scroll up a little. This is probably under my face anyway. So negative k over m. So the main thing that's, and it's okay, you can solve it this way and say that there's imaginary numbers in your constants. Electrical engineers love imaginary numbers because you can like do phase plots and all these like good stuff. But there's a slightly easier way, because really we want the second derivative to be opposite the first value. Like We want two derivatives of x to be equal to itself but negative. Make sense? Sine and cosine. Yeah.
Ah.
Yeah. So sine and cosine will take care of that negative sign for us, right?
This is better. This is better.
Rather than saying like my function is an e to the I root k over mt. It works, you can do that, but now all of your constants that you're solving for, those are all imaginary numbers. Just, it's a little extra work.
Just to be clear, the lambda equals square root negative k over m?
Yeah,
Okay.
yeah, negative, so root of the negative,
Plus or minus
yeah.
involved there.
We do need plus or minus, because there's two solutions, since
Okay,
it's,
so plus minus square root negative k over m.
yeah. So if we want to write out the full thing, there's a plus and there's a minus, because we said lambda squared is that, so we have two answers.
Thank you.
Yeah. And in general, for a differential equation, if it's a second order differential equation, there's got to be two answers to it, and they add up together. So instead, let's say x of t is, I'm going to put some extra constants in here, like a sine omega t, b cosine omega t.
Wait, what? When? Oh, with the phase.
No, it's diffy cube.
Oh, I was thinking physics when we had the electromagnetic wave.
So let's try this. Try figuring out what is, if A and B, I don't know what amplitudes those are yet. That's gonna depend on my initial conditions. Omega, like the frequency that this thing is gonna bounce back and forth. Right now, I don't know that. I just know that it does have a frequency. Like it's gonna be some kind of bouncing solution, and I'm gonna solve for that. Yeah.
Both a and b are constants.
Those are constants, yeah. So those are called integration constants. So it's just, they're placeholders to say, when I find a solution, I'll have to solve for those. So what is x dot and then x double dot? And then the next step is we'll plug it into that original differential equation and solve for, we won't be able to solve for a and b, but we can solve for omega. Start.
How did you know to do this? Sorry.
How did I know?
How did you? I
It
think
was
intuitively it's how it
divine
works, but
knowledge, yeah.
How did you take, like, you have x double dot equals negative k over m times x, and then you're like, all right, how do you know we need something that has double?
Yeah, so there are like more rigorous ways to like prove what function you need to solve a differential equation. Like there's infinite power series and stuff like that. But for the most part, like if it's linear things like this, it's always going to be some kind of e to the something t. So it's always going to be this, and sometimes it's imaginary, sometimes it's real. If it's real, then you have like either exponential decay or exponential increase. And if it's imaginary, then you have sines and cosines. So the quick way is just knowing, like, oh look, x double dot equals x, something times x, it's sines and cosines. And it's always the case. Like, it comes in lots of different forms. Like sometimes it's what is it? Changing current. This would be the inductor. Like if you had inductance for an electrical circuit, you'd have like change in the. It would bounce back. If all you had was an inductor and a capacitor, it would bounce back and forth as if it was same kind of thing, like a spring bouncing. And there's a lot of like linear differential equations like this where it's always like sines and cosines. Not like a great answer of like how do you know? Like how do you really know? Because really the way that you prove it is a Taylor series expansion of like, all right, I know it's a function, and I know it could be an infinite series of polynomials, and then you solve for what constants, and then things that you come up with are like, okay, the only thing it can be is a sine and a cosine. So it's a long way back to an intuitive approach of like, well, I know it's going to be bouncing, so sines and cosines? Yeah. Yeah, so how do you know is a good question, but usually you like convince yourself, and then in grad school you prove it to yourself. Like, go back. What did we end up with? Yeah.
Derivative negative sine thing. Oh, you have to do that. Okay. Derivative cosine, negative sine, and then derivative negative sine is negative cosine. Oh no, you just take the negative out, and then you get cosine. It works both ways now. Thanks, boss.
Oh.
I forgot what to do after.
And then take another derivative. How's that look? Does it match up with what you were working on? I know it's different, but I'm skipping. I'm doing a little algebra in my head. But it's not like, it's not incorrect. So the main thing that we're seeing here is like x of t is a sine plus b cosine. X double dot is negative omega squared. And this is x of t. Like that's the original x of t that we were trying to say.
Can I just go to previous class specifically? I can skip the radicals. Yeah. I can't.
Wait, why is just that component x of t?
Just that?
Like, is the negative omega squared part of the? Because it looks like you underline just the thing in parentheses. To get
Yeah, I did.
So why?
You
because that's
disagree?
original.
Is it?
What?
It's okay if you, yeah, you can call me out.
Yeah,
It's totally fine.
No, I'm not calling you out. I said
Yeah.
what's going on.
Yeah.
It's underlined because it's the same as the first one.
So when we took two derivatives, we ended up with the exact same thing we started with, but times a constant. And that constant is negative, which is exactly what our differential equation was. And now that whole like x double dot equals negative k over mx, it's not a differential equation anymore. It's just an algebra problem where I know there's some kind of function of x. If I multiply it by omega squared, that negative omega squared, then it is the acceleration.
Genius.
Pretty nice. We're doing like a semester's worth of differential equations all in like 20 minutes, so it's like makes it more fun this way. So we can just like get to the answer. Come on, let's get there. And we're skipping a lot of like background theory of differential equations and history, but it's all right. We just need the answers, right? We need like, here's the equation, plug in some numbers, get the answer. All right, so what is, we can't use this equation. We can't use our differential equation to solve for those constants because it's true for any constant. Like for any a and b, this is a true statement. But we can solve for omega.
If you assume a and b are 0, doesn't that mean the mass doesn't move?
But yeah, that's the uninteresting solution. Yeah. If a and b are both 0. So what is our omega now? What's that like? Root k over m.
Oh, did you cancel that? Did you cancel x of t on both sides?
Yes.
Yeah, since it has to be, like, x of t has to equal itself for all time, so you can't pick a constant such that those are not equal to each other, so we can divide through by x of t.
So that's an algebra step.
Yeah.
Okay.
Yeah. Yeah, that one's just, and that's what we're doing here, is like we're taking, if you can guess what the solution already is, then the whole problem is just like a couple of derivatives and then algebra, because you're saying like, I already know the answer, I'm just trying to plug some pieces in there. And I think this was sine, right? Then we know two things about this problem. One is that x times 0, x is 0. So x of 0 is 0. If I plug in zeros into my x of t, what do I have left? What's the sine of 0?
0.
0. Nice. So 0 equals a times 0. Not a great amount of information, but what's cosine of 0?
1.
1. So b is 0. We get no cosine amplitude here. But I know we're starting, I think we start at like 10 meters per second, something like that. But V0. And I already scrolled past it, but we'll just write it out. A root k over m and I already know b is 0, but that's all right. We'll write it out. All right, so now we still have cosine of 0 for this velocity term. So this all turns into 1. So what is my A? What's that, like? The amplitude of sine. Yeah, so whatever that V0 over root k over m. So I solved for b, solved for a. That means there's nothing left. Like I started with x of t is something, some kind of sines and cosines. I didn't know exactly what they would be, but now with initial conditions and my differential equation, I know that x of t is v0 over root k over m times sine root k over m t. Kind of like that. How's it look? So we went through like 3 different types of forces. Right now everything's just kind of moving left and right. But in general, most engineering problems are one of these 3 types, or like a combination of them. So I'm scrolling all the way back up. When there's like damping, where something is like the acceleration is proportional to velocity, there's some kind of exponential decay. Like your velocity is going to go to 0 at some point. Something's pulling out kinetic energy and turning it into something else. When there's constant acceleration, it's kinematic. Like it looks like the free fall kinematic problems. As long as you can prove like the forces are not changing, it's a parabola over time. And then in the last part, like anytime acceleration is a function of position, then it's going to be some kind of bouncing, like sliding back and forth or bouncing up and down, something. And there might be combinations of them, and you would add the multiple answers to each other, but that's for the most, 90% of physics stuff is kind of like that, at least like engineering problems. We like linear problems, linear differential equations, because they're easier to solve. And you can do a lot of good work with them. Create all kinds of stuff. Control theory and matrix, modern control theory. All right. So now we want to get everything into one place, right? Ah, come on, man. And then last one I'll just write. Yeah.
This is kind of an odd question. How do you do like the sines and cosines in Python if we were to do this in our Jupyter notebook?
Yeah, so I was gonna try like loading up a notebook and like build these 3 functions there. You can also use Excel, like any kind of plotting program is fine. I like Python. MATLAB is good. Octave is like the free version of MATLAB, or like whatever speaks to you is like something for comparing stuff. So move this one over. And then pop this one over. So we got side-by-side view. Actually, maybe we'll put this one over here and that one over there, right? Should have loaded this up before. There we go. And I'm just gonna make like a new notebook, just start from scratch. You don't have, like you could start in module 0 since we already had that like sliding problem. But just so we can see, like I usually have like NumPy, Matplotlib, and then I like the 538 plot style. So let me set up the things that I need to start. So I know my initial x is 0, my initial velocity, I think that one's 10, right? Mu, let's come up here. Mu is 0.5. B is 1. The units are kind of weird, but it ends up being like kilograms per second, so that it matches up. So damping is measured as like a mass per second, which kind of makes sense because it's like fluid flow, like how much fluid flow you need to like damp something. And then we got K as 4 newtons per meter. And do we need anything else? I think that's good, right? I guess the last thing we need is time. Go from like 0 to 3 seconds, because that's what we're trying to do. So creating a solution from 0 to 3 seconds, and we'll compare all 3 forces that are acting on this block. And now that I've like set up my variables same way that they're kind of set up in my like handwritten equation, it's just writing out that function as like a block of code. So I can say that it's x0 plus v0 times t minus mu. I guess I should write g in there too. So mu g, t squared over 2, cool. And I usually like to check like one at a time, just to make sure. So if I look at t and xa, we end up with that same problem where friction is now bringing us back towards us. So it starts sliding, but then at some point, because we're assuming it's constant, now it's moving backwards. So we can fix that.
Let's just get to the array of values. The line space at 0, 3, 30. So from 0 to 3 is 30 steps.
What did we do last time? You want to do the velocity part? So here, just same thing that we had done in that first homework, where I'm saying like, all right, if the velocity is less than 0, then just set it to whatever that max xa was. Oh, I guess I didn't write the mass, did I? M is 1 kilogram. Negative m times v0 over b. do like an exponent of negative b over m times t, and then minus 1, like that. Now I can see like difference between like friction, where it's a constant force, so it's a parabola, and then it just comes to a stop, versus a damper, which is like slowly, the slower I'm going, the less force it actually applies.
I can put all of them on the same graph.
Oh, if you just ask it to plot multiple things, then it's just going to keep dropping more stuff into the plot. Yeah, I think in MATLAB you have to say like hold on and then keep plotting, and then say hold off to say show it to me, like stop creating new stuff or start creating new stuff. Anyway, but Python's kind of nice. Like the more things you tell it to plot, the more stuff just gets shoved onto your plot.
Why is this one? Because what I'm trying to say is, for the first one you did like when velocity is less than 0, you just didn't do it for the second one because the velocity doesn't, it never starts like coming back basically.
No, the velocity never actually goes to 0 for that one. So we could check it though. So if I take a derivative, then I just end up with like v0 times that, and that -1 is gone.
Oh, I see.
And this is like general kind of first order differential equations. Like if you're saying that the derivative is equal to the original function, it's either going to be some kind of exponential increase if it's positive, or it's going to start at whatever value it was, and then as time moves on, it's technically never 0, but it gets close enough to 0, like at least for engineering purposes. By the time you get 3 or 4 time constants that way, you're at 0 for all intents and purposes, because it's an exponential decay. Yeah.
We submit the plot like with the work for the homework.
Yeah, and then submit like a plot with the homework kind of written work. So if you're using like a Jupyter notebook like this, then you can like just print off the whole notebook that way, or you can grab like a picture of your plot. Like
We're supposed to do print preview, right?
Print preview for the notebook, but you could like save. You can right click and save the image and say like here it is.
Wait, if you could preview the graphs don't show up.
I think you have to run the steps.
I did.
They should show up, right?
I got a nice preview ready.
Yeah, like if I say print preview, I get all the graphs.
They're just not showing up.
Alright, so last one was our sines and cosines. Sorry, I know we're out of time.
0.
V0 over square root k over m times sine and then it's catching up in a second, but one thing that is the same for all three, which makes sense, is like near time 0, they all have the same slope, because they all started with the same initial condition, just over time changes One's gonna keep bouncing back and forth, another one's gonna slowly come to a stop. Cool.
Wasn't that quite right?
And then zoom out so that this is like last thing we see on the stream for today.
You go file?
All right, thanks a lot. Oh yeah. Sorry, let me come. I can't hear.
How are we supposed to explain?
You're supposed to print as, but what it doesn't show the graph. I have print screen. That's not all. When you click for preview, it doesn't show the graph, right? That's what. Whatever, at least we're done.
I'm still gonna ask him. There was very much going to.
I'll just take a screenshot. Take a pic, bro. Can we get a voice memo with this?
Oh, we need to upload pictures of the other problems as well. Yeah. I gotta rewrite them all out.
Joining
They're all like 5 to 15 on this.
Oh, just take 5 minutes. To go to lunch after mechanics and then go at noon to the E2 thermo additional help.
Yeah, and that's fine. Wait, what's also? 3 and 4.
22.
I trust office.
That makes me easy. I'm supposed to
Like it never, like an E to the negative T, never really.
I have no idea what's
Yeah, do they also use like positions? Yeah. That one, I think the damper and the friction are about the same, they might be close to the same number. But it's not necessarily the case, like if there was less friction, yeah, same thing with damping, if you had more damping, it would go shorter. Yeah. Oh, really?
Yeah, that's what we were doing, so I just want to make sure that wasn't where I was supposed to submit. You click on.
Oh, yeah.
This.
No, that one's different, that's for like a graduate course.
Okay.
I don't know why that's in there.
Alright, so wait.
Yeah.
And then I emailed you about the past quiz. You said I had to submit an audio thing. I just didn't know like how do I do that?
You can use like your phone, record,
Like full video or like just
video is fine, yeah.
Okay.
Like you don't have to be like looking at the quiz.
okay.
What we're like, it's 10 to 30 seconds. So was the answer, yeah, are you sure about your answer? Did you have any questions? Was anything murky?
Right.
That's a quick like reflection.
Should I
would resubmit the question. Okay.
Thank you.
Yeah.
Catch up in a second. That was the last thing that I did. Quick question.